Okay, welcome back. So now we're going to talk about sets because we just saw it helps us with probabilities. What are sets? So we kind of saw sets before. Basically, yeah, we can put stuff in curly brackets. That's a set. Like the distinct objects inside without duplicates. So something like 1, 2, 4 would be a set of 3 numbers. Yeah, that's a set. So looks fairly similar to what we've already done. Again, there's the symbol omega, means all possible outcomes or all elements. There's a strange symbol here. That means subset. So A could be the same as omega. That's the equal part at the bottom. And it kind of resembles a bit this kind of smaller sign, but isn't really. It's more like a round shape, and it means it can be like less elements than the sample space, or equal. Then there's an empty set, two different symbols here, either empty brackets or this stroking through circle. Yeah, just nothing in our set. Okay, and now come two important ones. The first one is the union of two sets, and I'm gonna explain it. Just most of you probably know this, but just because it's so beautiful with the Venn diagrams, I can represent sets with a circle. So this is set A. Now you can imagine, let's say if this is A, then I've got the numbers 1, 2, 4 in this bag floating around. Then imagine a set B, and they can overlap in general. I don't have to, but I'll just draw it like this. That's my set B. And then I can ask myself, what's the union of those two? And the union means I join the sets together. So the red kind of follows set A, but then also encompasses set B. So the joint outline, this is A union B. If you have heard something about logic before, this is just a side remark, but there's logic and an ORs. So the logic OR is this one here, which looks like a little V. So we'll talk about that later. So if a number can be in A or B, then that's the OR, which looks like the union symbol. Okay, but that's just this little side remark. The other one that's interesting to us is the intersection A intersection B, and obviously I find that where we're within A and B at the same time, so this area here, which looks like a little lens, this one here is A intersection B. Two more. There's the relative complement A without B. So let me maybe produce this in, let me find a new color. Let's choose yellow. A without B. So obviously A, but then not the part that is shared with B. So it's this one here, the yellow one. It's A without B. And there's we can also replace the one with like other symbols, but sometimes it's quite useful. And there's the absolute complement, A bar. That's an interesting one. So A bar means omega without A. So we have to, when we talk about sets, we have to think about what is the sample space. Yeah. This is the sample space in this example. All possible outcomes in here. So A bar is everything that's not in A. Also in here. Yeah. More correctly, the frame is omega, everything inside, and what I've just drawn here is like omega without A. Okay, so this is Venn diagrams, and they're quite intuitive, and they help you visualize things. To take this further, to help us really with probabilities, we need to work with those symbols. And the question is, how do they behave? What are the rules they play by? Let's start with this one. So if I have the union A, union B, I can change the order. Yeah, that's what we used to. Something like, 1 plus 2 is also 2 plus 1. It's called commutative property, and it also holds for the intersection symbol. Yeah, I can change the order, no problem. We can also change the order in which we calculate things. So if it's all the same symbols, and that's important. So here I've got 2 union symbols, and it doesn't matter which ones I compute first. Yeah, I can first compute B and C, or A and B, it does not matter. This is called associative property. You know that from numbers, so 1 plus 2 plus 3 is the same if I calculate 1 plus 2 first as this one. And it also holds for all intersections. So those are really the obvious ones, but we have to state them because there's always a point where we ask ourselves, are we allowed to do this? So here are the rules. The interesting ones start when we mix intersection and union. So we've got union here and intersection there, and this is called distributive property because we can distribute the symbol out. So you probably know this from numbers. If I write 2 times 3 plus 4, then it's kind of obvious that this is 2 times 3 plus 2 times 4. Yeah. Same here, I can write A union B, and then here comes the intersection symbol, and then again A union C. Interestingly, so this one's probably still fairly intuitive. Interestingly, with the intersection and union symbols, it goes both ways. So what we can't do with numbers, this one here, which is definitely not this one. I just write it down. So this is just wrong. But with like union and intersections, we're allowed to do exactly that. So we can do it exactly in the symmetrical case, just the other way around. Distribute it out. So this was like reading from left to right, distributed out. We can also like see it as collecting it, which we're gonna use sometimes. So if you see two brackets here, and there's a union and then a union something else in both brackets, then you can combine it into one. Or if you've got an a intersection something, two different brackets, then you can combine them. So you can also go from right to left, yeah, combining things, very useful. We saw about negation earlier, the bar above an event. We can also double negate. Yeah, you know this from logic. I'm not lying means I am lying. So obviously double negation means double negated A is A again. Also the opposite of sample space, the complement of sample space is empty. What happens if we combine like union with a negation? What happens? And this is called De Morgan's law. This is one of the most useful rules that we have. So you'll have to remember this one. It's fairly straightforward. Basically what happens is let me put this unit in a different color. The negation, that one breaks up into two parts, but as a result the union symbol flips over and becomes an intersection. That's De Morgan's law. Likewise, if you have an intersection and a big negation, you split it up into two negations, but you have to flip the symbol. So out of an intersection becomes a union. Very simple, but very powerful. Sometimes as a little trick, this one helps. It seems obvious, but A union not A is everything. Yeah, if you visualize that, you've got A and everything that's not A is here. If you join them up, we get everything. There's omega. Also A intersection omega is A again, because you know everything that's in A is also in omega. Cool. Brilliant. So with this we can start doing some exercises. Let's have a look. I've given you a little expression here. Try and simplify that one using the above laws, and the outcome is one of the 4 alternatives I've given you. Yes, of course. A intersection B is the result. How come? So what we can do is, there's no obvious, like, you can try different sequences of doing things. It all leads to the same result. What I'm doing first is I'm splitting this negation bar up. Yeah, you can see, so I've got a separate one for A and B, which means my intersection got flipped. Now I've got 3 times the same symbol, so I can leave the brackets. I've got 2 times the same symbol, 2 unions, so I can leave the brackets off. That's my associative law. And obviously I've got 2 union A bar, union not A. I can just combine them to one. I've done it even differently here in my calculation. I first broken up the big negation here, so they all get double negated. So I've got A intersection B intersection A, and then you can leave one A off because yeah, you don't, A is already there and this is left over. Okay, well done. Let's do another one just for fun. So what's the outcome of this one? Perfect, yep. Why? What did I do? I used the distributive property, so you've probably seen intersection y in both brackets, so I can combine them. I get y intersection, and then I combine what is left there, and it's like x union x bar, and we know event plus union a negated event becomes a sample space, and then y intersection sample space is y. Perfect, well done. Okay, so now we know how sets work. We can calculate with them, we can deal with them in a normal mathematical way. Now we can look at probability of combined events. This is the next video. See you in a sec.